Hello everyone, welcome back. Today I'll be covering OSCE question and answer. Happy practice. So this figure shows the stress strain curve. What is the zone? Label A and B. As illustrated, and the answer is A. Elastic deformation zone. B. Plastic deformation zone. Discuss the definition of each zone. For elastic deformation, it is a reversible changes in shape to a material due to a load. Material returns to its original shape when the load is removed. For plastic deformation, irreversible changes in shape to a material due to a load. Material does not return to its original shape when the load is removed. Additional notes. In elastic deformation, strain is directly proportional to stress. This is known as Hooke's law. In elastic region, the molecular bonds are stretched but not broken. The gradient, that is the steepness of the straight line, correlates to the material resistance to deformation. This is called the Young modulus of elasticity. The higher the Young modulus of elasticity, the smaller the deformation produced for a given load. This figure shows a stress strain curve for a low carbon steel is a ductile material. For Hooke's law, the robot hook shows that the strain is proportional to stress is in elastic zone. Define A. Stress, B. Strain. A. Stress is force over area and has units of Newton per square meter. B. Strain is the change in length over original length. It has no units. It is usually expressed as a ratio or percentage. What is the breaking point or fracture point? The fracture point is where the material eventually fails. The ultimate tensile strength is the maximum stress that the material can sustain before fracture. Stress at the fracture point can be slightly less than the ultimate tensile strength because the latter can cause the material to neck, which reduces its cross-sectional area and therefore the force required to fracture. Again, the stress strain curve, you can see the ultimate tensile strength and the fracture or breaking point at the plastic deformation zone. You will see it throughout this video. What is Young modulus? Young modulus of elasticity is a measure of the stiffness, ability to resist deformation of a material in the elastic zone. It is calculated by measuring the slope of the stress or strain curve in the elastic zone. The higher modulus of elasticity indicates a stiffer material. This figure shows the stress-strain curve, and again, the slope represents the Young modulus of elasticity. You can see the Young modulus of elasticity is measure the stiffness, that means ability to resist deformation in the elastic zone. What is yield point? The maximum stress up to which a material undergoes elastic deformation. The yield point is the point on the stress-strain curve that indicates the limit of elastic behavior and the beginning of plastic deformation. Again, this figure of stress-strain curve shows the yield point. Additional notes. Yield point is the point in the stress-strain curve at which the curve levels off and plastic deformation begins to occur. The difference between the yield point and elastic limit. The yield point is fractionally later in the curve than the elastic limit. Elastic limit is the point at which deformation stops being entirely reversible, and the yield point is the point at which the material will have an appreciable elongation or yielding without any increase in load. However, these two values are virtually inseparable in most materials. Again, you will see our stress-strain curve. Another additional notes, what's the difference between offset yield stress and yield point? The yield point is that point at which the material starts to undergo plastic deformation. The offset yield stress is the stress needed to induce a specified amount of permanent strain, typically about 0.2%. For upper and lower yield point means for a certain materials, especially a low carbon steel alloys, the stress-strain curve produces both an upper yield point and a lower yield point. The upper yield point is the maximum stress at which deformation starts. A dramatic drop is then observed in the stress to the lower yield point. Eventually, the strain continues to increase. Eventually, the material is straightened by this deformation and the stress is increased with further straining. This means strain hardening. This is due to dislocation occurring in the material. Materials lacking this mobility are usually brittle. Again, this figure shows a upper and lower yield points on the stress-strain curve. Yield point is at which the curve levels off and plastic deformation begins to occur. Upper yield point shows a maximum stress at which the deformation starts. Next, what is creep? It is an increase in load deformation with time under constant load, or creep occurred when the applied strain is kept constant and progressive deformation of the material is observed. Deformation is permanent over time. Example in congenital talipes echonovirus management by using the Ponseti method. This figure shows a typical stress-strain curve of a tendon or ligament. The ultimate tensile strength, UTS, is the maximum strength that a material can withstand while being a tensile loaded. So, the toe region is within elastic limit. The linear is constant with Young modulus, that is the Ponseti region. The yield and failure region is where the macroscopic defects occur. Typical stress-strain curve on a tendon or ligament are shown by the graph just now. They have three distant regions. Initially, the collagen creams are stretched out and an increased number of collagen fibers and fibrils become aligned to the loading axis. This region is known as the toe region and normally extends to approximately 2% elongation. Further regarding stress-strain curve for tendon or ligament. The toe region lies within the elastic limit and thus the tissue will return to its original length when unloaded. Further straining brings the tissue into the linear region which exhibit a constant Young modulus. The stress-strain response mainly comes from elongating the aligned fibers and fibrils. Further straining induces the plastic deformation by interfibrillar and interfiber sliding, and consequently, the tissue does not return to the original length and structure after unloading. In the last region, the yield and failure region, in which the macroscopic defects occur, yielding begins as the slope of the curve decreases, with inevitable tissue failure occurring with further load. Again, this figure shows the typical stress-strain curve of a tendon or ligament, and regarding the toe region, the linear, the yield and failure region. Yay! We have reached to the end of this video. I hope it helps. See you in the next one. Take care and bye.